We saw in our vapor pressure video that the vapor pressure for a given liquid increased as temperature increased. You can see here that for water, in this blue line here, the vapor pressure is increasing as the temperature is increasing. Now, eventually, that vapor pressure will become equal to the external pressure, generally the atmospheric pressure. For example, eventually, you see that water's vapor pressure is equal to 760 millimeters of mercury. This is standard pressure. This is the pressure at sea level. And you see that water reaches this temperature at 100 degrees Celsius. There's no accident that the standard boiling point for water occurs when the vapor pressure is equal to the atmospheric pressure. You see, in order for a liquid to boil, in order for bubbles to form and continue to exist until they pop at the surface, there must be the same pressure inside that bubble as the outside pressure. The vapor pressure must be the same as the external pressure. So consider a case in which a bubble were to form, and this bubble, it did not have a vapor pressure high enough to kind of fight back against the external pressure. So the vapor pressure is less than 760 millimeters in this case. If there's not enough, if there's not that atmospheric pressure, then the bubble will not actually be formed. However, if the temperature is high enough so that the vapor pressure of your liquid is as high as the external pressure, then that bubble can exist, and hence that bubble will then, as it gets larger, break the surface tension of the water and then be released as it rises. So, in summary, in order to boil, the vapor pressure must equal the external pressure. The vapor pressure must equal the external pressure in order to boil. So we see then that water, its vapor pressure is equal to 760 millimeters of mercury at 100 degrees Celsius. And so when water boils, it occurs at 100 degrees Celsius, and as long as water is boiling, it will be at 100 degrees Celsius. But what if we were to change the external pressure by changing, say, the atmospheric pressure, by going to the top of a plateau? Let's say that you went to Denver. So this is several miles higher than sea level. There, the external pressure is about 630 millimeters of mercury. It's lower than at sea level, which is 760 millimeters of mercury. Now, having a lower external pressure in Denver, having only 630 millimeters of mercury pressure there, the vapor pressure inside the bubble needed to boil then is lower as well. It only needs to be 630 millimeters of mercury instead of 760 millimeters of mercury as at sea level. So, not needing as high a temperature, vapor pressure to boil, the temperature then needed to get to that vapor pressure is lower as well. You can see that for Denver, its vapor pressure is equal to 630 millimeters of mercury if its temperature is equal to 95 degrees Celsius, whereas for water, it needs 100 degrees Celsius in order to boil. So Denver's boiling point is 95 degrees Celsius, hence when water is boiling there, it will be 95 degrees Celsius. But what if you were to vaporize water within a steam cooker so that the pressure were able to build up within that steam cooker when the steam is formed? In a steam cooker, you can get up to about 1,500 millimeters of mercury pressure. And having these 1,500 millimeters of mercury pressure, the vapor pressure needed to boil then is about 1,500 millimeters as well. Now, in order to get this much higher vapor pressure, about 1,500 millimeters of mercury pressure, the temperature needed to get there is much higher as well. It can range all the way up to 121 degrees Celsius in order to boil within a steam cooker. And what that means then is that your Boiling water might be about 20 degrees higher in degrees Celsius than it was within a standard pot at sea level. But also, having higher pressure, steam can be kind of injected into your food that you're cooking faster as well. And so it might be said that you could actually cook food 3 to even 9 times faster in a steam cooker than in a standard pot. We've seen how having different external pressure affects the boiling point. But what about for having different liquids? Which liquids have higher vapor pressures and which ones have lower vapor pressures and then boiling points? So consider water. Consider ethyl alcohol and consider diethyl ether. Now, in order to predict the boiling points, the temperatures needed to boil to separate our liquid particles and turn them into gas, we need to consider the attraction between those particles. So first consider water. Now, water has hydrogens which are covalently bound to oxygens. Hence, those hydrogens are able to hydrogen bond with other water molecules. At here, 2 different sites. Considering this, there's a relatively high attraction between water particles because water is quite polar and also it has a significant amount of hydrogen bonding. Now, ethyl alcohol, ethanol, it has an OH group like water. However, it only has one OH group, and a large part of the molecule is relatively nonpolar and doesn't hydrogen bond. So having less hydrogen bonding and less polarity than water, it has a lower attraction between its particles than water does. So it has a medium attraction between the particles. And then we finally have diethyl ether. You note that there are no hydrogens on oxygens. Here, all the hydrogens are covalently bound to carbons. Not being able to hydrogen bond and not being as polar as water and ethyl alcohol, it has a relatively low attraction between its particles. Now, we could see actually that these attractions between the particles are very, very highly related to the heat of vaporization, which you'll be interested in if you're in my AP class. Now, the ease of vaporizing then is affected by this attraction between the particles. Now, water having a lot of stickiness between the water particles, so that it's difficult to separate the particles. In order to vaporize, they have to break these hydrogen bonds, which is difficult. Water has a low ease of vaporizing. It does not vaporize easily, whereas ethyl ether, having a low attraction between the particles, is able to vaporize, to separate its particles from each other fairly easily. And then, again, ethyl alcohol is medium. Now, the vapor pressure, then, of water, being that its particles do not vaporize easily, and hence will not give a lot of water particles in the gas phase. Instead, the rate of vaporization is so low that the number of water particles in the gas phase needed to equal that rate of vaporization is low as well in terms of their rate of condensation. We'll have a low vapor pressure as well. And then we can see with ethyl alcohol having a high ease of vaporizing, there's going to be high vapor pressure. There will be a lot of ethyl ether particles in the gas phase at a given temperature. So then we see then that water having a low vapor pressure is going to have a relatively high boiling point. Water having a low vapor pressure for a given temperature, you see it's lower here for, say, 35 degrees Celsius versus ethyl alcohols and diethyl ether's vapor pressure. Water, having a lower vapor pressure, needs a higher temperature in order to get to this atmosphere, the vapor pressure where it's equal to the atmospheric conditions. Whereas water boils at 100 degrees Celsius, we actually see that ethyl alcohol, it reaches that 1 atmosphere, or 760 millimeters of mercury, at about 79 degrees Celsius. And ethyl ether, that actually reaches that 760 millimeters of mercury at 35 degrees Celsius. 35 degrees Celsius. And so we can see then that water, which boils at 100 degrees Celsius, has a relatively high boiling point. And then ethyl alcohol boils at 79 degrees Celsius. It's a medium boiling point. And then ethyl ether boils at 35 degrees Celsius. That's a low boiling point. So ultimately we see that having a high attraction between the particles means that there's going to be a high boiling point. You need a high temperature in order to separate your particles, whereas having a low attraction between the particles means that there is going to be a low boiling point. Thanks for watching, guys.